The title of this next unit we're going to be talking about is graphing polynomial functions. Now, this directly ties into what we've been doing in the recent weeks, where we have been solving quadratic equations and other polynomial equations involving all the way up to the 5th and 6th degree. In some cases, we were using the quadratic formula for quadratics. Anything higher than that, we would factor by grouping, or we would do the rational root theorem. So all of the students should know how to solve each of the equations to find the roots of our functions. The first thing we're going to do today, before we start graphing any of the polynomial functions, is we're going to talk about the characteristics of the polynomial functions. As you can see, our essential question is going to be, what are some of the characteristics of polynomial functions? The students will investigate and explain characteristics of polynomial functions, including domain and range, the intercepts, the zeros, relative and absolute extrema, and intervals of increase and decrease, followed by the end behavior. The notes are fairly simple in this case, especially when it comes to the vocabulary with the characteristics. So after we finish doing the vocabulary and characteristics of the functions, we'll look at a few examples of odd and even functions and then move on from there to talk about end behavior. So there's three things that we're going to be talking about today. Talking about all the characteristics, talking about odd and even functions, and then ending the lesson by talking about end behavior, which definitely correlates to the characteristics and how graphs are going to be graphed on the polynomial functions. The first one we want to talk about is the domain. We know the domain is the set of all inputs, the x values. In polynomial functions, the domain is restricted to x values based on the graph. The second word would be the range. This is the set of all outputs of a function, the y values. The range is restricted to certain y values based on the graph. Intercept. This is another key characteristic. This is a point at which the graph crosses the x or y axis. And the zeros, things that we've been talking about for the last couple of weeks. The zeros are simply any values of x which make the function equal to 0, the x-intercepts. We will continue on with the characteristics to the relative extrema. The relative extrema are just extreme values of the function over an interval. Now, the relative extrema are extreme values of the function over an interval. The lowest point of an interval is called the minimum, local minimum, and the highest point over an interval is called the local maximum. We'll talk more about these in just a minute when we start looking at some of the graphs. An absolute extrema is the lowest and or highest relative extrema of a function. The lowest point of the graph is called the absolute minimum. The highest point of the graph is called the absolute maximum. Moving on to the last couple of things, we have the intervals of increase or decrease. Intervals of increase or decrease. A function has an interval of increase when its graph is going up. And a function has an interval of decrease when its graph is going down. Please keep in mind that intervals of increase and decrease are based on the x values, not the y values. We're talking about an interval, left to right. The end behavior is simply the behavior of a function's graph as x approaches positive infinity or negative infinity. All right, we have a few examples on the paper, and we're going to look at those while I work them out up here on the board. Starting with the domain of this function, we know that the domain always deals with the x values. When you're looking at polynomial functions, the domain is usually going to be all real numbers. In every case, as we can see, going from left to right, this is the case, so x is all real numbers. In this function, because our function never stops going down and never stops going up, never stops decreasing and increasing, our range is going to be y is all real numbers. The intercepts, we can see, are right here. One of the intercepts, now I realize that looking at this graphically, you can kind of have to guesstimate exactly where this function crosses the x-axis. But we could say that's close to negative 0.6. So one of my intercepts can be negative 0.60. We also have one at the origin. That would be 0, 0. And then we have another one here at 0.60. Those would be all of my zeros for the or my intercepts for the function. The zeros of the function are simply the places where it crosses the x-axis. This is x equals negative 0.6, 0, and 0.6. In this case, when we're talking about extrema, which are the characteristic that we want to talk about next, because our function does not stop in either direction, goes down to negative infinity and up to positive infinity, we don't have a maximum that is absolute or a minimum that is absolute. All we have is our relative mins and maxes, and they are right here. So there's a relative maximum and there's a relative minimum. For these, you just need to write relative, minimum, and just state the location. This is roughly 0.5 and negative 0.5. That is the coordinates, x, y coordinates for this relative minimum. We have relative max over on the other side here. And that is roughly about the same location. It's going to be negative 0.5, 0.5, or 1/2, negative 1/2 and 1/2. All right, the intervals of increase and decrease. We can just look at our graph. And please keep in mind that this always bothers a lot of people when they're working on intervals of increase and decrease for polynomial functions. This is an interval based on the x values. So what I like to do is just go ahead and highlight a line that shows where my function changes from decreasing to increasing and draw it all the way through the x-axis so I can get a feel for exactly where I'm going to be stopping my interval of increase and beginning my interval of decrease. When we're looking at the x-axis, this is negative infinity and this is positive infinity in this direction. My graph continues to increase as my function is moving from negative infinity all the way to this place right here. And this is roughly negative 1/2 or negative 0.5. So for my first interval of increase, I'm going to say negative infinity to negative 1/2. And at that point, that's where it stops increasing and it starts decreasing. Since it starts decreasing there, I go over to my intervals of decrease and I write down negative 1/2, and it stops decreasing here at this interval for x, and that is 1/2. At 1/2, I continue beginning increase, and it goes all the way to infinity. So as you can see from here, when x is 1/2, as I continue to move this way, my function is increasing. It's going up the entire time as x continues out towards positive infinity. Now, the end behavior. We've talked about end behavior in the last couple of years, based on which class you've taken, end behavior is simply where the function is going on its ends. It's not anything any more complicated than that. So let's talk about as x approaches negative infinity. As I head in this direction, where is my function going? My function is going down towards negative infinity. So as x approaches negative infinity, y is going to approach negative infinity. All right, let's talk about the other direction, because there are two ways that this function heads. This direction and that direction. As x approaches positive infinity, as I start going this way with my function, I notice that my y values continue to head in the positive infinity direction. So y approaches positive infinity. All right, so there are the characteristics of a function based on looking at the graph and moving on from there. I want to look at just a few more examples, just one more. Yes. Now, this function is a little bit different. You notice that the end behaviors are going in the exact same direction, so we know that the end behavior is going to change. There's also some other things occurring here, and you might remember talking about this before when we're talking about our zeros and our multiplicity and stuff. I don't want to get too far ahead of myself, but when your function changes direction on the x-axis, that's when you have an even-powered multiplicity. And we'll talk about those more later. At this moment, let's just cover the basics of the characteristics of a polynomial function. The domain is going to be all real numbers. Because the end behavior continues in this manner on both sides, our y values have been restricted. So when we're talking about the range, I want you to take close attention and look at your graph and say, all right, how low is my function going? Because that will tell you where your range has been limited to. So I look at my function and it goes down and up and down and up. But the lowest that my function can go is when y is 0. So I'm going to say that my range is y is greater than I'm going to say that my range is y is greater than or equal to 0. Now, looking at the intercepts, this should be fairly easy. We notice that this is at -2, this one is at 1, and then we have another intercept here, which is our y-intercept. Let's start with this one. This is -2, 0. This is 1, 0, and then my y-intercept ends up being 0, 4. Carrying from this, the intercepts, right down to the zeros. Remember, the zeros are the place where it crosses the x-axis or touches the x-axis. Two very simple zeros here, at -2 and +1. And that is it. Now, since our function has its end behavior in the same direction, we can determine that we will have an absolute minimum and a relative maximum. Now let's start with our relative minimums and our absolute minimums. This is the lowest point of the graph, and so is this one. So we actually have two absolute minimums. They just happen to be at these exact same places. And they happen to be our x-intercepts. So I just label them. The absolute minimums are -2, 0, and 1, 0. I have a relative minimum, or maximum, excuse me, at this point here. All right, at this location, we're up here at 5, and over here to about the -1/2 area. So once again, you can just estimate your relative maximum is going to be -1/2 positive 5. Now let's move on to our intervals of increase and decrease. When we start out our function from negative infinity, we notice that our function is heading down, it's decreasing, until it gets right here at negative 2. I'll just draw my little line to where I'm changing my direction for my interval. The next place that I change locations is there. So I have an interval from negative infinity all the way here. My next interval starts there and goes here, and as you can see, my function is increasing at this point. It stops increasing and starts decreasing from here all the way to this point, and then from there it increases again. So let's write our intervals of increase and decrease. We're starting with a decrease, so we're going from negative infinity all the way to negative 2. At negative 2, I start my increase all the way to here, and we said earlier this was negative 1/2. We will keep it at negative 1/2. At negative 1/2, I change direction again and begin decreasing until I get to this point at 1 where I start increasing again. And then from 1 all the way to positive infinity, I am increasing. So here we can see our intervals of increase and decrease. The last thing we want to talk about is in behavior. In behavior is always the same for the x values. The x values will always approach positive and negative infinity. It's the y values that we want to look at as x approaches negative infinity and as x approaches positive infinity. So as x is approaching negative infinity, meaning as I continue out this way on our function, we notice that our graph is going up towards positive infinity, which means that as x approaches negative infinity, y approaches positive infinity. All right, looking at the other side of the graph, as x approaches positive infinity, as I continue heading out in this direction, you notice that y is going up. So as x approaches positive infinity, y approaches positive infinity. These are two things that you will notice anytime we're talking about in behavior. We're just talking about where are the arrows going towards the end. All right, there are a few other graphs on the paper, but I was going to skip past those. If you think you need extra practice as a student, you may certainly work on those, and then you can check some of them with the free response that I have posted. All right, moving on past the characteristics, we also wanted to talk about even and odd functions today. And even and odd functions is not a relatively difficult concept. It involves just a few things that go along with the functions, but what you'll start to notice in these even and odd functions is certain characteristics that follow along with these and that build into some symmetry across the x-axis, the y-axis, and the origin. Let's start with the even functions. These are functions such that f of x equals f of negative x. For example, if we had the function f of x equals x to the 4th plus 2x squared plus 1. In order to test if this is an even function, you have to plug in negative x for any x values that we have. F of negative x. That would be negative x to the 4th plus 2 times negative x squared plus 1. Now we can simply use our powers of exponents and our properties behind them. And if f of negative x turns out to be the exact same thing that f of x was, then we have an even function. So let's take a look. F of negative x equals negative x to the fourth power. That is a negative number to the fourth power, which means this is always going to become positive. So that would be positive x to the fourth plus 2 times negative x squared. Well, negative x squared is just x squared, and then plus 1. So what you notice is that f of negative x is the same thing as f of x. So yes, we have an even function. One other thing that you might notice is that all even functions have all even exponents. It's just the way that they are made up. If you throw an odd-powered function in there, or an odd exponent, you're going to end up not with the exact same thing. So it just goes to show that even-powered exponents create even functions. Now, if you're like some students, you're thinking, well, what about this 1 on the end? If you remember correctly, we've talked about these before. This is simply x to the 0 power. So it still stays even. You have even exponent here, even exponent there, and then, of course, x to the 0 power. And anybody knows that anything to the 0 power gives you 1, and, of course, this will not change the constant here. One great thing about the graphs of even functions is that they are symmetric about the y-axis. One very simple example of that would be f of x equals x squared. This is the basic function for quadratics. It is even, and so therefore it would be symmetric about the y-axis. And you know that from graphing a quadratic, it would look something like this, where it is symmetric about the y-axis. All right, odd functions. These are functions such that f of negative x gives you the opposite of f of x. For example, if we had f of x, if we have f of x equals x cubed plus 3x, substituting in f of negative x cubed plus 3 times negative x. The checkpoint here is that if the f of negative x gives me the opposite of f of x, then I do have an odd function. Well, working this out, we have f of negative x equals negative x to the third power is still negative x, because that's negative x times negative x times negative x. And then negative x times 3 is minus 3x. As you can see, this is the exact opposite of the original function f of x, so therefore we do have an odd function. Now, one thing you probably notice about the odd function as well is odd functions have all odd exponents. So an odd function will not have any even exponents in it whatsoever. And if you look here, yes, this is an odd exponent. And remember that x to the first power is an odd exponent. All right, the graph of all odd functions are symmetric about the origin. Very quickly, we can look at a few examples. You could have f of x equals x. This is the basic linear function. It goes right through the origin. If we can draw correctly. Goes right through the origin and picks up every point that x does, so does y. There's also f of x equals x cubed. You know, this is the basic cubic function, and it goes directly through the x-axis, the right through the origin as well. All right, the next thing we want to do is look at a few examples of odd and even functions, and then explain why they're odd and even. Looking at number one, we want to determine whether it is an odd or even function. In this case, this is odd because all of the exponents are odd, and then it is going to be symmetric about the origin because it is odd. You just write origin. Looking at number two, there's an odd exponent, but don't forget this is an x to the 0, so that's an even exponent. If it's even and odd, then it's neither. Looking at number three, you can see that we have an even function, and it is symmetric about the y-axis. All right, the same follows for numbers 4, 5, and 6. You may look at those and work on those yourselves. We're going to move on and look at some graphs. Determine whether each function has symmetry about the y-axis or the origin. Tell if it is even or odd. All right, looking at number one, we can see that it has symmetry about the y-axis, so therefore it must be an even function. Number two has no symmetry, not across the origin or across the y-axis, so this would be neither. Number three has symmetry across the y-axis, the origin right here, and so therefore this is an odd function. Work on 4, 5, and 6, and then we'll talk about those three as well. All right, clearly we can say that number 4 is neither because it has no symmetry whatsoever across the origin or across the x-axis, y-axis. In number 5, we can see that there is symmetry right across the y-axis, and so this is an even function. Now number 6 is a little bit tricky, but you can tell that there is symmetry across the origin because it is the exact same in the first quadrant as it is in the third quadrant. You might recognize this function as f of x equals 1 over x. This is still to the first power, and so this is an odd function. All right, the last thing we want to talk about in this array of many characteristics, when we talked about all the characteristics of functions and then even odd functions along with that to talk about symmetry across the y-axis and the origin. I told you the last thing we wanted to focus on was in behavior today. Now, in behavior, graphically everybody can see in behavior. But algebraically, I want you to be able to notice in behavior just based on two things: the degree and the leading coefficient of a function. If you can get these two things down, graphing will become easier, and it will open your eyes up to how a function is going to look before you even have to graph it. These are keys to being able to graph polynomial functions as we head on in the next couple of days. In the first one, we look at the leading coefficient. It is 2. And we look at our degree, and it is even. because it is a 2. So these are the two things we're going to look at: the leading coefficient and the degree. If your leading coefficient is if your leading coefficient is positive and your degree is even, then your function is going to open up and you're going to have in behavior heading in the same direction. So, as x approaches negative infinity, y is going to approach positive infinity. As x approaches positive infinity, y is going to approach positive infinity. Even power tells me the in behavior ends up in the same place. Positive tells me that they're going to positive infinity. All right, let's scroll over and look at number 6. You have an even exponent degree. The degree is 2. And your leading coefficient is negative 5. So here we have a negative leading coefficient, but still an even degree. Well, as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches negative infinity. Because the leading coefficient is negative, our direction for the in behavior is going to be facing down. The degree has to be even, and a negative leading coefficient, your in behavior is negative infinity. If your degree is even, and your leading coefficient is positive, your in behavior will be positive infinity for y. All right, now we've talked about even powered functions. Let's take a look at the odd powers. And this is just ones where the degree is even. All right, in number 1, we notice that our leading coefficient is 1, but our degree is 3, which means it's odd. In odd functions, you might notice, thinking back to the linear function, in a linear function, the graph started in the 3rd quadrant and ended up in the 1st quadrant when you had a positive slope. When you had a negative slope, it was in the 2nd quadrant and going down to the 4th quadrant. The same thing is true for all odd-powered degrees. They will start in one place and end in the opposite direction. Looking at number 2, because the leading coefficient is 1, meaning positive, and the degree is odd. As x approaches negative infinity, y will approach negative infinity. As x approaches positive infinity, y will approach positive infinity. So, when the degree is odd and the leading coefficient is positive, our in behaviors correspond with each other. X goes to negative, y goes negative. X goes positive, y goes positive. The exact opposite is true, like on number 3, when your leading coefficient is negative and your degree is odd. In this case, as x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y approaches negative infinity. Just a flip-flop there. So let's recap. The leading coefficient is 2. Our leading coefficient is positive. The degree is even. Our in behavior is positive infinity. If the leading coefficient is negative and our degree is even, our in behavior is going to be negative infinity. If the degree is odd and the leading coefficient is positive, as x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches positive infinity. The leading coefficient is negative and the degree is odd. As x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, y approaches negative infinity. Alright, in this lesson, I know we've done quite a bit here. This is all the characteristics of polynomial functions. We needed to talk about the domain and range, intervals of increase and decrease, the zeros, x-intercepts, in behavior, and the characteristics behind in behavior, so we don't even need to graph it before we can talk about it. And we talked about even and odd functions that go along with these. And the even and odd functions play a bigger role than we think at the moment. And we will see that come to play in just a little bit as we start graphing polynomial functions. And that is it for this lesson. If there's any questions, email is always available. Thank you.